Right. So here's what we good. Here's what we have learned. 10.1 was good. 10.1 was intro to graphs and all the possible vocab you ever want to know, handshake and other things like that. The handshake theorem. And 10.2 was all about, I don't remember. Like walks. Is that the walks and paths and stuff? Yeah, so here's where we got all of our vocab, which we've all mastered, especially me, on That's a Joke. Walks, paths, cycles. This is supposed to be a new marker, but it doesn't work. Cycles, circuits, and there's one more. Trails. And here is where we explored things like the adjacency matrix, and there was that theorem about how if you make also, please let the record show that I'm wearing a graph theory polyhedra themed t-shirt for the third straight day. On Monday I wore my graph theory t-shirt, on Wednesday I wore my cube octahedron t-shirt, and today I'm wearing some other weird t-shirt. I think it's supposed to be Kepler, playing around with a bunch of shapes. So you're welcome. 10.3 was all about basically Euler. Make sure I want to say the right word. Circuits.
Ah, yes, that's
this was the day that was bad, but it was we got to the end, but it was done very inefficiently. And Hamiltonian cycles. And then 10.4 was about basically isomorphisms. Full isomorphisms. And then 10.5 is just like a lot of things. It's really like several sections all put together. And so I think I said for today, I said don't do any homework, right? Is that correct?
Yes.
Just like do the old homework. So the 10.5, the thing that happened in 10.5 so far, the thing that happened in 10.5 so far was we proved, we talked about planarity. And this actually happened in, not on Wednesday, but on Monday. This is when several of you were here. This is when we played the game at the end of class with the, it was like Shreya Sophia Emmanuel and the Water, Bacon, Love. And we seemed to suggest that we couldn't do it. And then last class we explored that a lot more carefully. We did the full-on proof with all the cases that K through 3 is non-planar. We talked about Kuratowski's theorem, proof in left for an advanced course, which is that there's always a K through 3 or K5 in there. And we haven't actually proven the K5. Yeah, we haven't talked about that, but I'm going to do that today. And then the other big thing that we did last class was we stated, discovered, discussed, and proved this thing which is known by various different names. Some people call it Euler's formula, or Euler's characteristic, or Euler's characteristic formula on polyhedra, whatever, which is that the vertices plus faces minus edges is 2. And as I mentioned in the video for last class, or just in last class, that this was originally stated as a theorem on polyhedra, but it was discovered, and there's an entire rich history of people's attempts to prove this, and it was discovered that actually it applies to a broader range of sort of shapes. And it was really not until the 18th century, 19th century, especially as those of you who took logic people started getting more flexible with their understanding of what geometry was, and it really became abstracted away from a theorem about the geometry of polyhedra to a theorem about graphs, their vertices, and the edges which connect them. Euler's original proof, which you could almost just do, it's very similar to the proof we did last class. He says, take some shape like a cube. Think of it as being sort of flattened out, or don't even necessarily flatten it out, just leave it as is. And then he did it he said, start removing things. And he said, look, every time you remove an edge, what happens? This is Euler's original proof-ish. Well, if you remove an edge, what did I just lose?
Your face.
I lost one face and I lost one edge, right? So we could minus an edge, minus one edge, and we can minus one face. That's one thing that could happen. Well, okay, let's do it again. Let's remove an edge. What did I just lose?
Another face.
Another edge and a face. Okay, now I'll do it one more time. Cha-cha, what did I just lose? An edge and a face. And now there are multiple ways to proceed, of course, from here. But one way we could proceed, this is the new exciting thing, is that I could remove this edge. But if I remove an edge now, which terminates in a vertex that is not connected to anything else in the subgraph that we are creating by removing these edges, now what I do, now I lose minus one edge and minus one vertex. Yeah? And now you just kind of keep on doing this, right? If I remove this one, I lose one edge, one vertex. If I remove this one, I lose one edge and one face. If I remove this one, I lose one edge and one vertex. If I remove this one, and then stop at some point. I don't know when you want to stop. Maybe go all the way. Maybe stop when you get to a polygon or something. And at any point, so theorem about any polygon. Let's just stop here because we're just doing this just a casual proof anyway. If you stop at a polygon, then talk to me about what you have when you have just a polygon. That's pretty much just a closed. Well, it's just a cycle is actually what we would call it, right? And in this cycle, there are two faces, so to speak, two regions, the inside region and the outside region. But then there's always going to be the same number of vertices and edges. And so if they're the same, if the number of vertices and the number of edges is the same once you get all the way down to a polygon, and the number of faces, so to speak, is 2, well then that kind of proves it, right?
Yes.
Okay. And if any polyhedron can be, by the succession of removed edges, converted into this, for which the relationship holds, then as at every moment we removed one edge and one vertex, or one edge and one face, then the relationship now just sort of worked the proof backwards, right? And just note that this relationship must have held at the beginning too. Cool? That's the super casual. I thought I was going to do it for the FIST kids proof, but I abandoned that plan. Of this formula. That's very casual. The proof we did last class was basically the same thing, but it was more formal. And it was more formal in the sense that we did not anymore purport to be proving something about polyhedra, but instead to be proving something about graphs. And let's see. I have, well, maybe I don't need my notes. Maybe I need my notes. What we did was we said, let G be, I can't remember the exact things I need to set this up properly, but let G be a planar, simple, connected graph with n greater than or equal to 3 vertices. And what we showed is that, okay, well, if it's planar, then we know that there are always going to be some certain number of regions, and, however, whatever. And we are going to count this as a region, this as a region, this as a region, and the outside as a region. And so, are you leaving it coming back or not? So now we have, this is all kind of a repeat of last class, right? The regions we sort of think of as being the faces, the number of vertices. I think, what did I call it? I just, did I call it N?
We called it N, yeah. N,
Yeah.
rho, and epsilon.
Epsilon.
I have this all written down somewhere. I'm going to find it in a second, but anyway. I called that N, the number of vertices, and the number of edges we called epsilon. And so the theorem restated as a graph theory problem is that the number N plus rho minus epsilon is 2. And this sort of transition into this being a graph theory problem is very interesting because note that like this graph, this one I'm looking at right now, is simple, planar, and connected, but it's certainly not a polyhedron, right? And by that I mean it's not the graph of a polyhedron. There is no polyhedron out there with 3, or I guess it would be, well, let me just double check. No, it just can't. Well, never mind. I'm not even talking about Platonic. I just don't think it's a polyhedron at all, right? Because there's like 2. This is like a little bit vague, right? But like the outside region would be one face, okay? But when you put it back together, there's like too much to be put back together. This is just like not a polyhedron. Who's with me?
There has to be an edge between them, which makes another face. Face move.
Wait, am I mistaken?
No, you're right. You're
I
right.
think you're right.
Yeah. I mean, okay, I can do even a better one. I mean, you know, this is like very, very certainly not a polyhedron because this literally just has 3 faces on it, right? But it is a simple planar connected graph. In other words, the sort of meta argument I'm trying to make is that, or this characteristic formula is like more broad than polyhedra. It is really best understood. It is best thought of as a theory of graph, part of graph theory. It's true about planar simple connected graphs. And now, like side fact, every polyhedron, when made into a graph, is a planar simple connected graph. And so it just sort of happens to fall underneath this. Are you sort of see what I'm saying? Oh, okay. Anyway, we proved it. The proof was done by induction. You can watch the video. We did it very quickly with like 7 minutes left from the bell ringing. We started it, but it's essentially very simple. It's just a slightly more organized way of doing kind of what we did over here, right? But instead of subtracting, we added. All right. Wait, I do want to find this piece of paper because I did write this out very neatly. So what I now would like to do is prove to you that there are only 5 Platonic solids. Probably could just wing this, but I definitely have notes on this topic. So I might just give you 1 second to find them. Okay. Or not.
I wanted to know why you couldn't have more Platonic solids. It's like 5th grade or something. Regular chaos.
I guess we'll know in a second.
Every vertex has the same number of Platonic solids.
Well, that's kind of annoying. All right. Good. All right. I'll just take a peek at what Gossett does. So here we go. Or I might have it written somewhere here, but whatever. Okay, good. Here we go. So we are now back to polyhedra, and what we would like to do is classify all of the regular polyhedra. What makes a polyhedron, or they're called Platonic solids, or they're known before Plato actually. The argument goes like this. So what is the Platonic solid? It's a polyhedron made of regular polygons, all the same kind of each one, with the same, with sort of full symmetry. So at every vertex, there are the same number of polygons meeting at that vertex. Okay, so let epsilon be the number of edges. So this is going to be the number of edges total in the polyhedron. Let V be the number of vertices. Let R be the number of faces. I don't know why it does this. And, okay, you know, also this is just the number of regions. And let N be the degree of each vertex. Or we could think of it, that's the graph theory way of saying what's going on. What's the sort of polyhedra way of saying what's going on? Yeah, this is the number of faces meeting at each vertex. Is that right? Yes, meeting at each vertex. Yeah, I guess it's like the same though, right? Because for every Okay, and then there is this sort of last parameter, which is b, the number of edges on each face, or bounding, the number of edges bounding each region would be the graph theory way of saying it. The Platonic solid way of saying it is just the number of sides of each polygon, right? Number of sides of each face. So like, is it triangles, is it squares, is it whatever? Okay, thanks. And so there are a couple of quick points to make. Man, I did really write this out so clearly somewhere. Oh well. First of all, there have to be at least 3 faces meeting at every vertex, or else it's just not a polyhedron. You cannot get 3, you cannot have simply 2 faces meeting at a vertex. So in other words, n has to be greater than or equal to 3. Agree? Rana, can you get down the Platonic solids? Also, that would be helpful. Then, the next fact is that b is the number of edges bounding each region. Like that also requires, you can only have like at minimum triangles, right? So b is also greater than or equal to 3, because like the smallest kind of polygon is like 3 and up. Okay, and then next, what's another point to make? I will get those as well. Yeah, so now, okay, well, I guess this makes more sense to sort of just do the argument first. Okay, so here we go. What are the relationships between all of these things? One relationship is we can find the relationship between V, N, and E. So V, N, and epsilon rather have a relationship. What is their relationship? Well, V is the total number of vertices, and it's regular, and you know the degree of each vertex, then just count all of the degrees of all the vertices. What happens when you take the sum of the degrees of all the vertices? What do you get?
Epsilon over 2.
Twice the number of edges. That's just the handshake theorem, right? Okay, but now, of course, we have said that because it's regular, that the degree of each vertex we've called n, right? And also, how many vertices are there? Like v. This is like a strange kind of way of saying this, but like, right? If the number of vertices is v and the degree of each vertex is n, then if you just multiply n times v, then you will be double counting the number of edges. Do you want me to say that one more time, or are we good? Say it one more time. Yeah, if you take the number, go to every single vertex on the entire polyhedron, count the degree of each vertex. Okay, so you've counted the number of edges that are adjacent to that vertex. By doing that, that's n times v of them. You've double counted the edges.
Okay.
It's just a handshake theorem, but thinking of it now is happening on the polyhedron. Cool? All right, so that's one relationship. But there's a similar kind of handshakey theorem or relationship between epsilon, r, and b. Because, well, now look at every region. Region, face, same thing. And we can count the number of edges in each region. Sorry, the number of edges bounding each region, I should say, right? So yeah, so right, so you have R regions. Each region is bounded by how many edges? B. But if I multiply the number of faces times the number of edges that surround each face, what have I done? I've double counted the edges, because every edge is a member of 2 faces. So this is also double counts the edges. Okay, so we get, who's with me? Everyone? Okay, good. So we get this relationship and this relationship. Okay, but then also every polyhedron if you do that thing where you remove one face and sort of flatten out, is a planar simple connected graph. And so, Euler's characteristic formula is applicable. And so, okay, I keep changing my notations slightly, which is, I'm just following Gossett in this sense, so sorry. But yeah, if I have V total vertices minus the number of regions, which is R plus, minus the number of edges is 2. Agree?
Yeah.
Okay, and so now what I want to do is solve for R. Oh yeah. Yeah. So just like now, we're just gonna we're gonna turn this into a formula involving B, N, and epsilon. She's not here. What we want is this to be a formula with just B, N, and epsilon. And so I guess I'm gonna solve for R and let's just do it. So we solve for R here. So R is 2 epsilon over B. And now stick that in here. And we're going to solve for V here. V is
2 epsilon over n.
Yeah. V is 2 epsilon over n. And we're going to stick this here. And I think that's all I have to do. Let's see what happens if I do that. Yeah, that should work, right? I'm kind of like don't understand.
2 epsilon over n plus 2
Oh,
epsilon
yeah,
over
that's
n.
good. So what we get is V is 2 epsilon over n plus 2 epsilon over B minus epsilon equals 2. Is that what you just said? Okay. I mean, this is just kind of algebra 1 as soon as you have these relationships. Cool. Waiting for a cool. Okay. So now, all right. So now it's sort of convenient to kind of write this out more nicely. So one thing we might do is like divide all 3 sides by epsilon. Seems like a good idea. Or 2 epsilon. All 3 sides. Sorry. Divide both sides by 2 epsilon. If you do that, it gets pretty, right? Because this becomes 1 over n. This becomes 1 over b. This becomes, and this becomes 1 over epsilon. All right. So, and actually, I'll add 1/2 to both sides, and then I'll kind of pause here. All right. So this is the like sort of magical relationship between the degree at each vertex, the number of polygons meeting at a vertex, the kind of polygon under discussion, and the total number of edges. And one way to sort of look at this theorem is to note the presence of this 1/2, right? N, B, and epsilon are all positive. So if this is 1/2, one observation to make about like N and B is they can't be that big, right? If N were like 6 and B were like 7, then that just is impossible. Which is another way of saying you can't have, which is, okay, maybe should we do the 5th grade proof real quick? That there are only 5 Platonic solids? You want to do, let's do the 5th grade proof. The 5th grade proof goes like this. This proof we like literally did with, just did this in 5th, right?
Yeah.
With the girls. So what we said is, okay, background knowledge about polyhedra. If you have a triangle, every angle is 60 degrees. If you have a square, every angle is 90. And then if you have a pentagon, you can do a little math and you can find that these are all 108. And then if you go up to hexagon, then these are like 120, right? And so if you now sort of consider this sort of chart or something of the number of, let's see, I guess I'll do it like this, B and N. So now let's just consider sort of all possibilities. This is the middle school proof. Well, we already agreed that they each have to be greater than or equal to 3. You can't have just 2 faces meeting at a vertex, and there's nothing less than triangles. So B is like 3, 4, 5, 6. These are the possibilities, right? In other words, triangles, squares, pentagons, hexagons. Okay, and then over here we'll count the number that are meeting at each vertex. And so again, you have 3, 4, 5, 6, etc. But then, like, it turns out, like, only some of these are possible. So let's just do it. If you have 3 triangles meeting at a vertex, is that possible? Hold it up, proud. What do you get? This is just the tetrahedron.
Don't drop the tetrahedron.
Okay, don't drop it. Just like bring it out into the open so we can love it. What if you have triangles but 4 meeting at a vertex?
Yeah.
That's the octahedron. Agreed? What if you have triangles 5 meeting at a vertex?
Icosahedron.
This is the icosahedron. All right. What if you have triangles 6 meeting at a vertex?
6 times 60 is 360, so you just get flat.
Yeah, you just have flat now, man. Yeah, if you have 6 triangles meeting at a vertex, then that uses up like all 360 degrees, and it's just flat and it can't curve. And so what you actually get is just like like a so-called Platonic tiling. It's the Platonic tiling of triangles, and there's just triangles everywhere, like 6 meeting at a vertex, and it just goes on forever, but like you don't get a polyhedron. Okay? Okay, cool. But it's like a tiling. And certainly more than 6 triangles will not fit at a vertex, not in Euclidean geometry, but in hyperbolic geometry you can for sure do that. Okay, what about squares? Can you have 3 squares meeting at a vertex?
Yeah.
Yeah, that's called the cube. It's just like is the cube. Can you have 4 squares meeting at a vertex?
Yeah.
It's plane.
Yeah, but only, then you just get this infinite, you get a tiling again, but that's no polyhedron. And then this one, these just can't be done, right? These would be, again, you can try to fit 4 squares together, 5 squares together at a vertex. In non-Euclidean, hyperbolic geometry you can do that, but in Euclidean geometry, we like to do stuff like that. All right, how about pentagons? Can you put 3 pentagons together at a vertex?
Yeah.
Yeah, you can. Then you get the dodecahedron, and then here, now already you just can't do it, right? If you try to put 4 pentagons together, you go over 360. So again, this can be done in hyperbolic geometry. And then what about hexagons? Can you fit 3 hexagons together? Yeah, that's like again going to be like a tiling, and so that's it. And then more than 6 hexagons together at a vertex can't be done in Euclidean geometry. All right, that's the 5th grade proof. We're relatively satisfied. Why are we even doing anything else if that's so done? Because no, it is fine as a theorem of geometry. It's kind of fine, but what we are going to do sort of now is to like invoke the sort of combinatorial properties. We sort of started getting into this conversation a little bit last class, right? Which is that like, right, the cube, I don't really care about the fact that the faces are all regular. What I really care, what matters about the cube to me, maybe if I'm in a certain mood, is just like the combinatorial properties of the cube, which is just like the number of edges meeting at each vertex of the cube. In other words, take any sort of cube, take something which is like combinatorially or topologically equivalent to the cube, which would include like all rectangular prisms, or even parallelepipeds or whatever. Anything whatsoever, any shape whatsoever, which has 6 faces, each of which is composed of quadrilaterals, which have regions of degree 4. They would all, if you count those as all like the same thing, then that's what's being reflected in this proof. And what we're showing is that even by that relaxed standards, there are only 5 shapes out there which are possible, because otherwise you sort of violate Euler's characteristic formula. Okay, just to like finish this off, there's this really smooth way of finishing it, but I guess I'll just bumble through it. So we just have to go, right? We have to say a couple sort of smart things, which is that 1 over n plus 1 over b has to be greater than 1/2. Strictly greater than, right? Okay, and so just by a exhaustive categorization of n's and b's, like what are the n's and b's possible which are bigger than 1/2? There's like not that many, right? So like n equals 3, b equals 3. Let's see, what do we want to do? Let's do the b's first. So if b is 3, then n can be 3, and that's the tetrahedron, I know, but I just like to think of it this way. So starting with triangles, if b equals 3, n equals 3, that satisfies this. Check. If b equals 3 but n equals 4, that satisfies this, because a third plus a fourth is bigger than 1/2. If b equals 3 and n equals 5, that's a third plus a fifth, which is 8. Yeah, so maybe we should be doing these as we go, right? This is, what I get then is 1, maybe I'll just write this down, right? I get like 1 third plus 1 fifth equals 1 over epsilon plus 1/2. This one was 1 third plus 1 fourth equals 1 over epsilon plus 1/2. This one was 1 third plus a third equals 1 over epsilon plus 1/2. And like, let's just do these, right? If this is true, then this is like 2 thirds. 2 thirds minus 1/2 is 1/6. Can we do this algebra in our heads? Because I've run out of board space. Can you close the Panicam? Okay, good. 2 thirds equals 1 over epsilon plus 2. If you subtract 1/2 from both sides, you get 2 thirds minus 1/2 is a sixth. And so you get 1/6 equals 1 over epsilon, so you get epsilon equals 6. And so in fact, what shape is this? The tetrahedron. So that is one of the n and b combinations which can possibly satisfy this starred formula in the box. And because it's greater, the left side is greater than 1/2, and the algebra tells you that epsilon is 6. And so what we have now is the shape in which, there are instead of triangles, there are 3 triangles meeting each vertex, and there are 6 edges total. That's just the tetrahedron. Cool? Say cool.
Cool.
All right. What if you have a third plus a fourth? Does that satisfy the fact that the left-hand side is greater than 1/2? It does. And now you get like a third and a fourth is like something. What is that? 7/12. So if you subtract 1/2 from that, you get 1/12. And so this is epsilon equals 12. What shape is this? This is the octahedron.